Hello guys, welcome to Self Help Maths Academy. Let us continue the discussion of infinite series. In this, there is a theorem. If a series summation un is convergent, then limit of un as n tends to infinity is 0. If it is convergent, then its limit is 0. The question is the converse is true? That if the limit of the sequence is 0, then is that series is convergent? So let us see how do we prove this particular result. In order to prove this, let us start with the given thing. So they have given that summation un is convergent. Okay. So in order to understand this, let us start with the partial sum. Let Sn be the nth partial sum. Okay. So nth partial sum of the series, partial sum of the series summation un. Okay. So let us consider that this Sn be a partial sum. Now, given that summation un, the series is convergent, this is given. So when we know that by the previous video, we have seen if the series is convergent, then convergent implies it's a partial sum. Sn is also convergent. So this implies your partial sum Sn is convergent. Okay. So when we have got the summation is the series is convergent, then the partial sum of that series is also convergent. All right. Now this implies when it is convergent, it implies limit Sn as n tends to infinity. It should be finite. When it is convergent, it should be finite and it should be unique. All right. So let us say we consider this as some yes. Okay. Let us say that it is equal to some yes. Now similarly, this is a partial sum of nth series. If I consider the partial sum of n minus 1 term as n tends to infinity, this is also equal to finite and it is equal to say yes. So now our Sn is the partial sum up to n terms like u1 plus u2, say un minus 1 and un. So it is a partial sum of n terms, whereas Sn minus 1 will be the partial terms up to n minus 1 terms. Okay. So let us take this way. Now if I take the difference between them, Sn and Sn minus 1, if I take that, when I take the difference between them, this cancels the terms, u2 cancels, un minus 1 cancels. Now we just left with the term un. So this is our difference between the partial sum is equal to un. Okay. So now once we get the difference between them, let us now take the limit on both the side as n tends to infinity. This will be say Sn minus 1, Sn minus Sn minus 1, and this is limit un as n tends to infinity. So this is nothing but what? Limit un as n tends to infinity is equal to separate the limit Sn as n tends to infinity minus limit of Sn minus 1 as n tends to infinity. So here we have already known, because it is convergent, the partial sum of Sn and Sn minus 1 is convergent and it is finite and unique. So we know the values of them is already equal to yes. Okay. So therefore this is equal to yes and this is equal to yes. So this is equal to what? 0. So this implies we started with limit of un as n tends to infinity. We got it as 0. So this is what we wanted to prove. We started the theorem by saying that the given sequence, the given series summation un is convergent. Okay. And we got a conclusion that limit of un as n tends to infinity is 0. So this implies if the series un is convergent, then the limit of the series as n tends to infinity is equal to what? 0. So this is what we have proved. Now they ask us whether the converse of this theorem is true. So the converse of the above theorem is not always true. Okay. So it is not always true. So when you say that it is not always true, so that means you need to give the counter example. So when I say the converse of the above theorem does, I mean, like, it's not always true, that means if the nth term may tend to 0, okay, the nth term, the nth term as n tends to infinity, it may tends to 0, okay, as n is tending to infinity, even if the series is not convergent, even if the series is not convergent. Okay, so let us see some example in that case. If I have 1 over 2, 1 over 3, and so on, say up to 1 over n, and it's a infinite series. In this case, what happens is, this particular sequence is diverges. This sequences diverges through limit. This is a divergent sequence. If but actually, though the limit as, say, the nth term is 1 by n as n tends to infinity, so limit of 1 by n as n tends to infinity, this will give you 0, though the nth term tends to 0, but this sequence is a divergent sequence. So this is one counter example which we can quote for this particular above theorem. All right, so now let us discuss another test. Now we will discuss one by one another test. So here we will be discussing the comparison test. So the comparison test, it says that if summation, the series un and vn, they are the series of positive terms. Okay, if they are series of positive terms, and if I have summation vn is convergent, if this summation vn is convergent, and there is a positive constant, say k, the positive constant, say k, such that your series, the un is less than or equal to k into vn, this is true for every n, then summation un is convergent. Summation un is convergent. So what this statement says? It says that there are two series, summation un and summation vn. Both the series are of positive terms. That means each and every term is positive here. And they've given that summation vn is convergent, and there is a positive constant k, such that your the nth term of un and nth term of vn are connected by this relation, that un is k times less than or equal to k times of vn. This is true for each n. This implies your u1 is less than or equal to k into v1, u2 is less than or equal to k into v2, and in general un is less than or equal to k into vn. If that is if this relation holds, this is true for every n, then your summation, your series un is also convergent. This is the comparison test. Why we are comparing here with the vn, and then we will try to give the idea about the un. So let us see how do we prove this. In order to prove this result, we'll start with the un. Let us consider un. Your un is say u1 plus u2 and u3, say up to un, and vn is v1 plus v2, v3 up to vn. Okay, so as we know, now let us consider un again. This is our u1, u2, say un. As our un is related to vn by this result, I'll replace this each term by, say, because your u1 is less than or equal to k into v1, your u2 is less than or equal to k into v2. So therefore what we do, we try to write it here. Your u1 is less than or equal to, this is k into v1, k into v2, so on up to k into vn. Okay, so this is what we will write for each term. Now here we can take this is equal to k, we can take out, so this is simply v1 plus v2 and so on up to vn. So here we got what we got is, this is nothing but what, v1 plus v2 up to vn is nothing but our vn. So your un is equal to k into vn. So this is less than or equal to k into vn. So let me take this as 1. So given that since your summation vn is convergent sequence, okay, it is a convergent sequence. This is given, all right, in the statement. Therefore, the sequence, the summation vn is convergent. Therefore, the whole sequence vn is convergent. It is convergent and hence it is what? Bounded. So it is convergent as well as bounded, because you can see that your sequence un is less than or equal to k into vn. All right. So therefore, each and every term is what? It is bounded by each and every term of your un is bounded by this. So hence it is bounded. Therefore, I can write this is by 1. So here un is less than or equal to k into vn. This is true for every n. Okay. So there what we can write here is un is less than or equal to k into vn. Now this should be less than or equal to, since your vn is bounded by this. So let us consider that it is bounded by some k, k naught. So I can replace that by k into k naught. This is true for every n. So now let me write it as un is less than or equal to k into k naught. Okay, this is true for all n, and k into k naught I will write it as one number. Let me write it as some k for all n, where k into k naught I'm taking as some capital K. Okay. Now if you observe, your un is less than or equal to some k, where k is any number, right? So that means each and every number, every member of your un is less than or equal to k, means your un is also what? Bounded. Bounded above, because it is having the upper bound here. K is being upper bound. So therefore your sequence un is bounded above. It is bounded above by k. If you want, you can write. So also it is bounded above. Also your summation un is a series of positive terms, right? Series of positive terms. Positive terms. So therefore, since it is bounded above and it is nothing but it is a series of positive terms, so clearly we can say that your sequence un is monotonically increasing. Okay, so it becomes monotonically increasing sequence and it is bounded above. So we know that one of the property, if any sequence is monotonically increasing and it is bounded above, then that sequence is convergent. So therefore summation un, the sequence un is convergent. If the sequence un is convergent, then the series of the sequence un is also what? Convergent. It's also convergent. So here what we did is we just started with the comparison theorem. So we were knowing about un. We have two particular series here. We know about vn, and we also been given with the relation of un and vn by the element k. So we can justify and we can say that the series un is also what? Convergent. So this is a beautiful theorem which we also call as comparison test. This is one of the comparison tests. So maybe in the next video we will discuss the different comparison tests and the example related to these comparison tests. Okay, so I think with this, let us conclude today's discussion. Maybe in the next video I will discuss about the examples related to this particular test. Till then, take care.